Welcome to my talk about event-driven microservices. A little bit about me. My name is Urs Peter. Because of my gray hair and 20 years in the industry, I dare to call myself a senior software engineer. In my daily job, I'm with my hands in the dirt, building applications. Besides that, I'm also a trainer at the XCB Academy, where I've created by now quite a variety of courses. Among others, event-driven architectures, which I'm going to talk today, but also about Kotlin and Scala. Kotlin is really my favorite toy, so I'm also a Kotlin certified trainer, and I'm also a co-organizer of Kotlin Dev Day coming up at 24th of November. So this was the slick advertisement. So, I do not present this presentation totally on my own, because Jens will join me. Who is Jens? Jens is the CEO of Average Inc. And Jens is not really technical. So he's the guy who will ask the stupid questions, which of course tend in general to be not that stupid. So he's the one who will challenge my statements I make today. Say hi to Jens. Okay, so now I'd like to know a little bit more about you. You can do grave waves, that's what I've already seen, but I would like also to know a bit more about your background with microservices. So who of you has the pleasure or the burden to work with microservices? Wow, that's quite a few. Excellent. Okay, who of the ones using microservices are happy with their microservices? That's a bit less than before, right? Okay, so I see there is still room for improvement. By the way, who is still doing monoliths? Classical monoliths? Okay, 20%. Cool. All right, so now I know a little more about you. Let's see if we can tailor that to you. In order to understand why the things are the way they are, it's important to look at the past, because the shortcomings of the past shape our current solutions. And that is particularly true for system architectures. Computer engineering started around the 60s, and we had monoliths. Well, why monoliths? Because there was no other way to do applications. You had these huge mainframe machines, which probably would fit on this stage, but definitely more machines than that. And the only way to deliver software was on these machines, so monolith was the only choice. Around 2000, we got these service-oriented architectures, and since about 10 years, we are dealing with microservices. So, why didn't all the hands go up when I said, do we still develop monoliths? Apparently, that's not the best way to do things. And that's not entirely true, because when you start out with a monolith, well, then you tend to get quite happy faces. Why? Because reasoning is quite simple. You have this single code base, and the only thing you have to care about is the database. It's very consistent, because you have normally a relational database that has transactions, so consistency concerns are really not there. It's very reliable. As long as my application server keeps on running and my database, woohoo, we are always up. And that's mostly due to the fact because we do not have a large amount of distributed computing to take care of. So far, so good. However, businesses grow, and with it, the new features that are added to the monolith grow. And you definitely will reach a stage when the faces get a bit more stiff about their monolith, till you hit the stage where you created this huge tangled monster that is very hard to understand, difficult to scale. Most of the time, the database is the bottleneck for your monolith, and scaling databases can be very costly. But also, extending features, especially when multiple teams are working on the same monolith, well, that's not a very pleasant thing to undergo. The same is true for deployment, because you have to ensure that a consistent whole needs to be delivered to production. And especially when multiple teams are working on such a monolith, then you have a lot of coordination going on, management, and so on. So once you've reached the spaghetti stage of your monolith, then I would advise everyone in this room to search a new job. Run away. And it's not only we as technicians that kind of realize that things aren't that great, it's also the business, Jens, in that sense, that recognized it. He sees that, well, time to market isn't that great. It's a very expensive system. And last but definitely not least, developer happiness will suffer too. Okay. Well, then these service-oriented architectures came in. Why? Actually, SOA was the first attempt to decomposition a larger whole into more manageable subparts. That was the first take. So what we see here is we had this one thing, now you made some splits. Not really small units, but it could still be quite significant. The point is that these two units still had to talk to each other. So all of a sudden you got remoting. And in the SOA area, this was facilitated by enterprise service buses. So their communication went through. So the advantage was that, well, it is a bit better to understand because you now have smaller units, right? Probably also a bit easier to extend and deploy. So these were the gains you had with this kind of architecture. However, especially this service bus proved to be a single point of failure in many regards. From a runtime perspective, scaling these buses was expensive. Also, from developer perspective, so running your thing on a local machine isn't great either. And also from a configuration perspective. Normally, a team was responsible for the service bus, and when you need to have a service talking to another service, your request somewhere got the end of the backlog until it were up there, quite some time could pass. So all of a sudden we are facing distributed computing, which we didn't have a lot in our monolithic area. And also these web service protocols didn't really help. They were quite complex. And because we are dealing now with distributed computing, availability and reliability all of a sudden got an issue. And the SOA still tended to use a single database, well, different schemas, but the same database, and scaling the database, again, was a very costly endeavor. Well, eventually we got to microservices, and microservices actually have quite a lot in common with service-oriented architectures because they learned, or I should say they should have learned from the shortcomings of service-oriented architectures, kept the good ideas, and re-architected the whole thing to fit modern infrastructure like cloud, containers, serverless, NoSQL databases, and so on. And if you then architect the thing right, then you get systems like that, but that we'll see later on. So here you have Jens again asking, yeah, what makes a microservice? From what I've told you by now, I think it's still kind of hard to get an idea of what is then a microservice compared to a service-oriented architecture component. Well, an easy way to figure out how a good microservice should look like is by looking at its design principles. So let's go through them. The first one of the very crucial ones, is isolation. So what do we gain if we have true isolation? What we gain is that we get scalable units. Because if you have an isolated thing, you can scale it, doesn't affect other things, so scalability is right away available. What we also gain is resilience. What is resilience? Resilience means that if one part of a system fails, it doesn't affect the whole. It's like the bulkheads in ships. When one bulkhead is filled with water, the ship still continues floating. And what you also get if you have true isolation, meaning you don't have many dependencies to other things, you can have continuous delivery, which is also true for independent development. So that's quite an important characteristic. Closely related to isolation is autonomy. A microservice should have all the information, all the data available to make decisions autonomously, which implies that a microservice can publish its own API. Well, the most troublesome word in microservice is the word micro, right? Because it implies something about size. The way I think you should look at it is not looking at its size, even though it's related to that, but rather look at its single responsibility it needs to fulfill. And, well, how do you define its single responsibility? How do you do that? Normally, domain-driven design can help with that. you have these event storming sessions that allow you to deduce the so-called bounded contexts. And the bounded context in general can be translated to a microservice. But that's actually a topic of a different talk. So why is single responsibility a good thing to have? Well, when you have single responsibility, then you can scale your features in parallel. So multiple teams can work in parallel on features because you only focus on a single responsibility. When it comes to size, there are still some heuristics to kind of double check whether you kind of match the single responsibility more or less right. A microservice normally should fit in one person's head. It should take weeks and months to develop, and it should be developed by at most one team. If you can tick these two boxes, more or less, then there is a chance that you have the single responsibility right. Okay. Another important principle, which is a logical consequence of autonomy and isolation, is exclusive state. So every state change a microservice undergoes should only and exclusively go via its API. Which means that if you have multiple microservices writing to the same database schema, you violate this principle. And most probably you will encounter that this violation causes some harm. The default way to exchange data between microservices should be asynchronous message passing. Well, more on that later. For now, just let it sink in. The last, which is not really a concern most of the time, is location transparency. What is location transparency? It means that we address certain microservices in a virtual way rather than a static way. So instead of having a static IP address, we have some DNS, and this DNS ensures that it will be routed to some healthy instance. That's location transparency. Why we need that? If you want to scale things, you have to you should not know how many instances are behind it, which you would get, for instance, with a DNS approach. And what you also gain, of course, resilience, because multiple instances can be there. Modern infrastructure, Kubernetes, clusters, and the like just fill that in for you, so most of the time this is not really a concern. Okay, so now we know these principles. Let's design a microservice that fulfills these. Wait a minute. Jens has something. What does he have? He says he has a blueprint from his architect department with these microservices. He wants us to have a look. Okay. So Jens intervenes, no problem. So this is his take of a system. Apparently has 3 microservices: CRM service, order service, inventory service. Let's see how the flow goes. So you submit the order. Then I fetch customer data from my CRM service. Well, I need, of course, customer data to process the order. Then I call the inventory service. I ship the goods. And once the goods are shipped, well, I call the order service again to update some state. Yeah, what is wrong with this design? Is there something wrong? Well, there are only a few arrows, but unfortunately, there is quite a lot of stuff wrong with this design. Can you see it? Okay, let me help you a bit. Let's challenge it, looking at different characteristics. First, look at coupling. So what happens if one service is not available? Say, if the CRM service is not available. Well, I can process orders, right? Because my order service depends on the CRM service. Of course, I could mitigate that, right? I could make the CRM service highly available, which is costly. I could implement some retry mechanism, which is complex. I could add some caching. Again, another layer of complexity that is added. So what we see is with these synchronous communication patterns, what we cause is tight coupling. And in general, tight coupling is bad for our reliability and availability, especially when one service depends on many others. Let's look at the control flow. What kind of control flow do we get with this approach? In our example, and this is what you also will see with this approach, is that a few services or one single service is responsible for the whole flow. When it comes to the state, we see that in this design, well, every microservice has its own database, so that's fine, and the state changes actually go through their APIs. What we see in this particular case is that we get a centralized control flow. And this can have the disadvantage that you can get a concentration of complexity in one of the services. Now let's look at how our whole architecture evolved, because of course we won't end up with 3 microservices. The business events, new stuff, new microservices will be added. Environments tend to grow. So how does our architecture evolve? Well, say I have this analytics service that, well, to do its job, it needs data from other services. There are 2 ways to bring the data to the analytics service. Either we kind of push it to the analytics service, or we let the analytics service fetch the data from these 2 services. No matter which approach we choose, we will introduce more coupling into our whole mix. And what's even more is that either we increase complexity, because now all of a sudden this order service, event service has to call other things which increase complexity, or we increase load for different services. Like if analytics service fetch data from order service and event service, then they have to handle more load. These are the choices we have. So what we see in this approach with the synchronous communication patterns is that we get an interdependent evolution model. And that means that the more things we add to the mix, the more complexity and tangling we introduce. Or in other words, in the long run, our reliability and availability of our landscape will decrease. So, let's step back, right? Why did we create this microservice architecture in the first place? Well, we had some shortcomings in our monolithic area. So that's why we did that. The only problem is that we still have these problems now. We still are quite difficult to scale. So if the order service, for instance, scales, well, the CRM service should scale with it, because otherwise it can't handle load. And we might forget that. And in production, we see that, things still start to break. Extending is also an issue, because we are so dependent on each other that most probably have to deploy multiple microservices at the same time to kind of get these new features up and running, which again requires coordination. However, in the monolithic area, we still had some advantages. Remember, there were some green things, some happy smiling faces with regard to consistency, reliability, and not a lot of distributed computing. These benefits now also are gone with our distributed monolith we've created, because distributed computing causes exactly the disadvantage we have there, an unreliable system, and consistency is all of a sudden a big concern. So when we still had some sleepless nights in our monolith, now, well, we have a legion of these spaghetti monsters, which is not definitely what we want. So who of you recognizes the trend? Of course, this is a bit exaggerated, just to make my point clear, but who kind of sees that? Realized that in his own experience. Okay, quite a few hands up. Cool. So, if no hands would go up, then, well, I could stop talking. That's kind of good to go on. So, what went wrong? And again, a very easy way to figure out what went wrong is to look at these principles. Which principles were violated? Let's assume that the single responsibility principle wasn't really violated. Let's assume that we did this right. And when we look at the portions we see here, okay. Can also be a problem, of course, but for this particular example, let's assume that's fine. Location transparency is handled by our Kubernetes cluster, no issue there. Exclusive state also seems to be okay. Every microservice has its own database schema who's responsible for. So apparently, the problems are more on the left. When we look at isolation, we see that the things we created are not isolated. They're highly dependent on another. They're also not autonomous. The order service requires quite some dependency of other services to fulfill its task, so it's not autonomous. And I didn't see any asynchronous message passing so far, only synchronous communication. If we try to bring back this whole thing to a one-liner, we could say that the root cause of all evil is that we introduced tight coupling between services. So now you might be tempted that tight coupling is a bad thing. That's not the case. Think of it. If you have an application and a database, these two things are tightly coupled. But that's exactly what we want, because tight coupling allows us to derive a lot of value from one another. And it's also not an issue because our application manages the skew evolution of the data I'm dealing with. It's most of the time managed by one team, so tight coupling is fine. However, if you have tight coupling across services, then things start to get worse. And I assume you might have the same question like Jens, how can we do better? I like this quote. It's said to be from Albert Einstein, but of course that's something you really never can prove. That's what people say, but you don't know. Nevertheless, I think it's a very good quote, because it basically says that the means we use that cause certain problems are probably not the means we can use to solve them. So we need a different approach. So that's why it's time now to introduce you to Mr. Event, the superpowers of Mr. Event. So what is an event? Well, it's quite something simple. It's a fact that has happened. And this is nicely depicted in the way we name events. The fact, in this case, the order, has been placed, the thing that has happened. So what does an event reflect? It reflects the state of the world. So not the state of mind, the things we want to happen, no. The things that has happened, the way the world looks right now. Does it have intent? No, it just tells you, this is your new reality, good luck with it. Processing is generally asynchronously. And do events expect replies? No, they're always fire and forget. However, events can trigger other events to happen or other actions. But the event by itself never expects a reply. Events come with two very crucial capabilities. Like the guy delivering the thing you just bought on your door, rings the bell. So an event can serve as a notification. And this notification we can use to trigger other actions. At the same time, when we get this parcel delivered, we also get an invoice delivered, right? There is also some data associated with it. So an event can also serve as a data replicator from system A to system B. Okay, so let's put these two new things into our design we just had before. Well, that's kind of hard because before we can do eventing, we most probably need something like a messaging middleware layer, like Kafka, for instance. I have to say that I've created very successful event-driven architectures without messaging middleware. It's really possible. The only thing you need is a database and a bit of advanced directive code. Then you can perfectly have event-driven approaches without messaging middleware, which even has quite some advantages. But again, that's a story for a different talk. For now, let's assume we go a bit more mainstream. We do something like Kafka. That's the solution that's probably most used with these kind of architectures. So what the order service does, instead of calling the inventory serving once it has placed order, it simply emits an order placed event. The inventory service then consumes this event, eventually ships the product, and once it's shipped, it emits another event, order shipped. The order service consumes this event and does whatever it needs to do, update state. So here we clearly see that we have used an event as a notification. Okay? Quite straightforward. Let's look at the synchronous customer relationship. How could we solve this in an event-driven way? It's probably not very straightforward, right? But it's not that hard. So instead of having the CRM service exposing an API, whenever a change happens for a customer, it simply emits events of the delta, like customer registered, billing address changed, or simply the whole customer record. Of course, it's APIs, you need documented and so on, but that's what it does. Then the order service can consume those events, and based on these events, can create a local view of the data it needs to fulfill its order logic. So when now the order comes in, instead of querying the CRM service, simply queries its own database, which has to do anyway. Yeah, indeed. Why is that better? We simply can challenge the thing like we did before. We talked about coupling, control flow, and evolution. So let's look at coupling. What happens if one of the services is not available? If the CRM service is not available, nothing happens. It just keeps on working. Which is quite nice because the CRM service by now could be a very simple thing, could be even a small monolith or whatever it is. We don't have to scale it to the same level like the order service because they're independent now. So what we see is that when we introduce an event-driven approach, we automatically get loose coupling, and by doing so, we get autonomy and isolation for free. Which, of course, is very good for our availability of the whole business process. Let's look at the control flow. And there are some variations to that, more on that later, but if we look at the control flow we get with only using events, this is more or less what you get. So who is in control of the process? Well, it's not really one instance anymore. It's the different microservices owning a portion of the whole. And the true flow the true flow we have is basically depicted by the flow of events. So this is our control flow. So what we get is a more collaborative, decentralized control flow. Instead, what we had before, a centralized control flow. And the advantage is that we can spread complexity evenly, so no concentration in one spot. And of course, for our reliability, that's awesome. If one system is not there, the whole business process just keeps on working. Okay, so now let's look at our third characteristics, system evolution. We had this analytic service, remember, we added to the mix. So how does this impact our existing services? Well, there is no impact, right? We just start consuming the events the orders emitted, and we're fine. So what we get, instead of this interdependent evolution model in our synchronous case, we now get an independent evolution model. So the more things we add to the mix does not increase complexity. So this is more or less the story. And of course, it helps if you can offer some more tangible patterns how you could implement this. And the good news is, Jens, yes, there are some patterns available. Time, of course, is limited. We have 50 minutes. So I had to make a selection. And the patterns I'm going to show you today are the, as I call them, the three musketeers that can get you extremely far. I would say the most important patterns you should consider in case you suffer from the shortcomings we showed in the beginnings. The first pattern we're going to look at is CQRS. Who has heard of CQRS? That's good. So it means that this knowledge is already quite broadly available. However, before we're going to look at the pattern CQRS, let's one more time very clearly picture what we're dealing with here. What we're dealing with here is that we live in a world with decentralized data. So when you have an order to process, we need customer data. And if I do not own this data, I need to get it from somewhere else. So the conclusion of this is that, if you like it or not, data dependencies are always hard. There is no way around data dependencies. The way we solved it in our take one is that we kind of fetch the data at the moment we need the data. So when the request came in, we did the call to the CRM service to fetch customer data. And we've seen that this can cause quite some trouble. So what we need is something different. We need to invert the whole thing. And the nice thing is, we're all developers. We actually already know how to do this. I said, I'm the guy with the gray hair. I experienced the introduction of this particular means, which is called inversion of control, right? Dependency injection. I think all of you know what dependency injection is. So dependency injection means that when I get, for instance, when I have a service and I want to call a database, I use a data access object for that, a repository. And it's already there when I need it. I don't have to fetch it first or kind of look it up in a registry. It's already there. Exactly the same thing we can do with data. So inverting the whole thing, meaning that we push the data to the place where it's needed. So when we need it, it's already there. So instead of having this arrow going out, let the arrow go in. And some sort of formalization of this pattern comes in the form of CQRS. So what is CQRS? Or let's say, what is it not? In a traditional application, you normally have a domain model. And domain model needs to fulfill two purposes. First of all, it needs to fulfill our writes, so our updates are domain model, and it also needs to satisfy the read part. And this doesn't always go that well together, because the read part sometimes has different needs than the write part. That's why we create those queries with joins and sometimes even materialized view to kind of get these things still performant. Because the needs are different, but we only have one model. So CQRS takes a bold stance saying that, well, let's separate the two. Let's have a model only for writes, and let's have a model only for reads. The read model, of course, is deduced from the write model, right? I mean, it doesn't invent it by itself, the data where it gets from. But these models still can look quite different. So what we get then is that all commands would go by the write model and all reads would go by the read model. So how do we get then the data from write to read? That's still something we have to facilitate. This is where our events come in. There's something very important to realize when you choose for this pattern, which is explained in a minute. So let's see this pattern in action. So we get a request, and instead of only updating our domain model, we now also create an event, which is some sort of delta, what's happened to the domain model, and this we emit to our messaging middleware. Then the same application consumes this event and updates the read store. And now you already can see that, well, this is not instantly. It's not atomic. And that's the point here. If you embark on CQRS, you have to deal with eventual consistency. It's not strong consistency anymore, it's eventual consistent. Is that a problem? The good news is, most of the time, it's not a problem at all. When you order something on the internet, I never had it that once I pressed send, that someone ringed on my doorbell, here's your product. No, it always takes quite some steps to process an order. It's very normal that things eventually get delivered, but not right away. And should you think this is a problem, go ask your PO, and your PO will definitely, most of the time, tell you that, yeah, when you look at it, it's not really a need that we are really strong and consistent. Eventual means sometimes seconds or minutes, right? It's not hours. But nevertheless, you have to take care of that. CQRS becomes particularly interesting when you apply it across microservices. Because now, like in an example of our analytics service, we now can consume those events from different services and build an aggregated view of data. And by doing so, we even can unleash new capabilities of our business because we can combine things all of a sudden. What's also important to remember is that we do not have to store the read or write model in the same database. We can have a relational database for our write model and a indexed search database like Elastic for our read model. So we can even choose which kind of database we can choose the database that fulfills our needs best. In my professional life, I've come to realize that this notion of replicating data is kind of a hard thing for people, especially architects, old architects, to accept. And even so, if you think of it, it doesn't make sense, because if we fetch the data at the time we need it, with all the misery thereof, we've just seen before, versus that the data is already there, but replicated for us, doesn't make a difference. Data dependencies are hard. So it shouldn't be a big thing to accept. Nevertheless, you can get in discussions. Once you've embraced it, then you definitely will be rewarded. I assure that. I started doing this about 6 years ago, and I'm very happy with it. So, should this be a problem, it might help if you have this mantra next to your bedside table, and when you repeat it enough and apply it, these phases will be yours. Okay, here we have Jens again, and he's skeptical. Of course, I understand, he's a manager. And okay, I mean, he has a point, right? Consistency is a concern. If we replicate data from A to B and things get inconsistent, so not eventually consistent, but really inconsistent, we're in trouble. So the least thing we want to happen is that the data in the source will deviate from the data in the target. That's from an engineering point of view, a very important thing we need to manage. And the good news, of course, is that, well, that's the next pattern I'm going to talk about. Distributed transactions 2.0. Unfortunately, in practice, I often see the following happen. The developer just makes some domain model update, which is persisted in a relational database using transaction. And he's read the CQRS pattern, so now I have to create an event and put it on my messaging middleware. Well, not in a transaction. So if I cannot put my event on a messaging middleware, that's where my inconsistency journey starts. And good luck figuring out what went wrong. So don't do that. And if you did, go fix tomorrow. Eventually, you will run into that. Maybe the older guys among us, they might think, okay, whoa, I know something. We have these distributed transactions. Who knows what distribution transactions are? Two-phase commits. Okay, there's so many old guys in the room. Wow. So for the ones who have not heard of them, distributed transactions is some sort of transaction manager that can commit to two resources at the same time, right? So you can have a messaging system and a database, which all take part in this two-phase commit, and then it will either be committed or rolled back. That sounds like a very good idea. The problem only is that in practice, it's often not. Well, for one, most modern messaging middleware products do not support distributed transactions, like Kafka. There is no distributed transaction for that, so there's no option. And should your product support it, then it's not such a great idea. What I've seen in practice is that things can really crash badly. It takes a lot of time because there's a lot of chatting going on to commit those transactions, so your performance will really suffer. And also your availability will suffer because such a transaction manager always needs to have two resources up and running. We're talking about the database management middleware, so I assume they're up and running, but still, you introduce a lower amount of availability. So what can we do then? It's not that hard. There are two patterns that help us achieve that. So instead of committing our domain model update, we commit the event that goes with it in the same transaction. And where do we commit this thing? In a so-called Outbox table. So the event goes in the Outbox table and the domain change in our domain model part. And of course, this all happens in the same transaction. So we are consistent. What we have then is the so-called polling publisher. So what this thing does is it kind of polls the Outbox table. When it sees, oh yeah, there is a new event I haven't yet put on my messaging middleware, I take it and put it on the messaging middleware. Wait a minute, you might say. Wait a minute. Now we're still dealing with the database and the messaging middleware. So it can be that I get the data out of the database, push it on the messaging middleware, and then I'm not able to commit in my Outbox table that I've put this event on the messaging middleware. And we're still inconsistent. Make sense? That's true. That's true. However, there is a very simple way around it. So if the consuming part of our event ensures that it has at least once delivery semantics in place, nothing will happen. That means that the consuming part of our events must somehow ensure that it knows that I have consumed this event before. In practice, that's not really hard to implement. Normally, it's some ID, you check whether you have had it, and everything is fine. Large infrastructure that embrace this way of processing, well, this is the default design pattern, at least once delivery. Okay, so then let's move on to our last pattern, which is the Saga. And the Saga is something between coordination and consistency. Let's more look at our alternative flows. We've placed an order. The inventory service consumes this event. It says, OK, I have to ship. Oh, it's not inventory. I cannot ship it. Well, what do you do then? From a business perspective, according to Jens, what we need to do is we need to issue a refund for the customer, and we need to somehow inform the user that the order cannot be published. That's the so-called compensating action we need to take. And this is exactly what our Saga is taking care of. So the Saga's responsibility is to ensure the consistency of the business process. So not the technical consistency, but more the consistency of the flow you want to handle. That's what the Saga is supposed to do. So whenever something fails, then this compensating action need to be initiated so that our whole process still is consistent. Well, how can the Saga do that? We've seen that these distributed transactions probably won't work, so Saga only work with local transactions, the only thing they have. So in that sense, the local transactions, they are atomic, of course, but the business process as a whole is not. Because when you have to cancel some reservation from a web service you consume outside your company, there's no way to do a transaction with that. So how can a Saga ensure consistency for the business process? Well, that's quite simple. It's a matter of writing code. So this is how you ensure that things are consistent from a business perspective. You have to type it. There are two flavors of Sagas. One we've already seen, actually, which is the Choreographed Saga. The inventory service in the happy flow would emit a order shipped event. Now he's not able to do that, so he cannot ship. So what does it do instead? It simply emits a different kind of event, saying, I couldn't ship the order in a order failed. And then, for instance, the payment service knows, oh yeah, order failed, then I have to do a refund. And it also emits another event, I have refund this client, which is then consumed, well, for instance, by the order service to update something. That's the choreographed Saga, and that's something you get out of the box. There's nothing special you need to do in place. You simply use events to handle these situations. It really helps to look at the advantages and disadvantages of this approach, because it's not full of advantages. There are definitely disadvantages associated with that. One advantage, of course, is that we're still perfectly loosely coupled. Everything just definitely will succeed. The disadvantage, however, is that when our order flow gets very complex, well, reasoning can be difficult, because most probably rules will be spread across different systems, something that can happen quite easily, especially when things start to grow. You also probably have to shift around transient state, so to say, of the order so that every component can make decisions, which is also something you maybe do not always want. And if you want to know what's the current state of my order, then good luck. Kind of have to maybe have another system aggregating data. So when things start to get complex, you might run into these problems. The good news is that you also have a different kind of Saga, which is the Orchestrated Saga. And the Orchestrated Saga works with a so-called Saga coordinator. And the Saga coordinator has, as it's called, a order Saga log. So this is a persistent log that keeps track of all the steps of a certain order. And the Saga also knows what to do in case things go wrong. So the compensating actions, it knows how to take them. Which still can perfectly happen in an event-driven way, right? We do not have all of a sudden the need to do this synchronously. No, you still can just emit events. It's what we see here. So if order failed, then the Saga knows, yeah, order failed, then I have to issue these events, make sure that this and that and so on happens. So the advantages, of course, is that because it's a single unit, reasoning is simpler. All the possible flows for a certain order is in one place. So when you have to adjust something, you do it at this place. And as long as things do not get too complex, well, other services also most probably can be a bit simpler. They just execute certain things and not too much logic will be brought to them. And that can be at the same time disadvantage that you again get the case where you have this concentration of logic in one spot, which can again limit the amount of new features you can develop because every change then has to go through the team that does the order saga. However, from a runtime perspective, you're always safe because you use events. In a runtime perspective, that's fine. It's more when you add new features, then this can get in your way. So, this brings me to the conclusion of this talk. Should your microservice architecture be in trouble, then I advise you to remember the JFall 2022 event to embrace events. And when you ask the three musketeers to help you, start out simple, small. You definitely will see that the parts where you applied them will tick all the boxes of the principles we've seen. And of course, ticking box and principle is never a goal by itself. But what you will experience that your microservice architecture really will pay off, giving not only you a good night's sleep, but also enables your business to successfully grow and do its thing. Thank you.